Algebra 2, Chapter 10, Section 4, Solving Exponential Equations. A population is given by P equals 149 times 2 to the 1/9 to the t, where t is in years. When does the population reach 596? So to find the answer to that, we need to solve this exponential equation, which we have not talked really about how to solve this explicitly. To start with, we're going to learn how to solve these kinds of equations the hard way, and then later on in Chapter 11 we'll learn a much easier way to solve this kind of equation. For now, we have a few methods. The first is we're going to divide both sides by 149 and see if there's an obvious power of 2 here that we can use to find the answer. So dividing both sides by 149, 596 divided by 149 is 4. And 4 is the power of 2, so we can solve this with our algebra we know now. 4 we can write as 2 squared. So we have 2 to the 1/9 t is 2 squared. Now we have the bases the same, so for these bases, so this equation to be true, the exponents need to be equal. So 2 needs to equal t over 9, which means that t has to be 18. So that's the answer. In 18 years, the population will be 596. Suppose, however, we don't have a power that is an even power, an integer power. So suppose the number of bacteria in a colony in millions is given by 5 times 2 to the t. So quantity, what are we going to say? Let's get B for bacteria, is 5 times 2 to the t, where t is in hours. How long will it take for there to be 70 million bacteria? Remember, this is in millions. So we're trying to find the answer to this equation. Dividing both sides by 5, 70 over 5 is 14. So we have 14 equals 2 to the t. There's no integer power we can write. 16 would be 2 to the 4th. And 8 would be 2 to the 3rd, so we can guess that t is somewhere between 3 and 4. Okay, so let's go over that logic for a second. 2 cubed is 8. 2 to the 4th is 16. So we can use a method called guess and check. So we have, to get a close answer, we have that if t were 3, we would get an answer of 8 for this part of the equation. So the 5 is already taken out by dividing our desired answer. 70 divided by 5 is 14. So we're trying to find when the total factor of growth is 14. We see that when t is 3, we get something less than 14. When t is 4, we get something more than 14. So we can guess around and try to find something that'll come close. So maybe if we did 2 to the 3.5 power, we would get something close to 14. So let's try that. Use a calculator to find 2 to the 3.5 power. 11.3. That's closer to 14. It's about, we'll write about 11.3. What about 2 to the 3.75? So I'm just going in between, trying to shrink the possible interval where the answer might be. 13.45, so we're getting closer to 14. What about 3.8? Since we're already close, 2 to the 3.8 power is 13.93. We're getting much closer. We're not quite to 14. What if we try 2 to the 3.81? Well, we would get 2 to the 3.81, 14.03. And suppose this is a good enough answer for our application. So we could say 3.81 hours. is how long it would take to get to 14 million. This seems very tedious, and it is, and your calculator, when we learn how to solve these using our calculator, it's actually doing a similar process, but it's able to keep narrowing this interval automatically by making its own calculations to get a very good answer. It's very close to the right answer. So we can guess and check, and we could also use a graph. So if we have a tool or a way of creating a graph, which we could do by evaluating at different points like we did here. That's how we make a graph. So suppose we evaluated a bunch of points, these blue dots, and connect them with lines and make a graph. For this is a graph of a bank balance earning 3% interest given by this formula. T is in years. So T is in years. And our bank balance, of course, is in dollars. So this could say dollars everywhere. So when there's been no time passed, we have $22,000. So suppose we want to project out in time, given our 3% interest, what our bank balance is, when our bank balance is going to be $30,000. So we can find on the graph 30,000. Fortunately, it has this nice dashed line. And we can look and say, well, it looks like it's between 10 and 11 years when we get to 30,000. So let's say it's about 10 and a half years to get to 30,000. What about 40,000? So 40,000, follow the dashed line over. It's pretty close to 20, much closer than 21. So we'll just say in about 20 years we'll have $40,000. And what about 50,000? Following the line for 50,000 over, looks like it's right around 28, about, not quite 28 years, so we'll just call it 28 because that's what we're approximating here. So about 28 years we'll have $50,000. And without solving an exponential equation, we can learn a lot about the solution just using some logic. So we can answer these questions. Is the solution x positive or negative? So here we have 2 to the x is 12, which represents growth. And we have a number that's bigger than the starting point. The 2 represents growth, so this has to be positive. X must be positive. So this kind of logic can help us narrow down where to even start guessing. Here we have 2 to the x is 0.3. We have growth, but we have this is actually a smaller value. So we'd have to use a negative x to get the answer. So the answer here is negative. C, 0.5, this represents decay. To the x is 0.3. So our initial value here is 1 in each of these so far. So we've shrunk from 1 to 0.3, but we're decaying. So that would be a positive value of x. Since we're decaying, you think about the graph, we're decaying. So as x goes up, the output's going down. And then D, we have to figure out, we have 3 as our initial, and then now we're talking about 12, so we have more than we started with, but we have decay. This is less than 1, which means x has to be negative. The solution x is in which interval? Less than -1, between -1 and 0, between 0 and 1, or greater than 1 for the following equations. So A, we have growth. We started with 1 thing. So when will we have 3 things? Well, when we have 1 unit x of growth, we'll have 4 times more. So after 1x, we'll have 4, which is more than 3. So when x is 0, we have 1. When x is 1, we have 4. So we have to be in a case of we're between 0, x is between 0 and 1. B, we start with 5. Now we have 26. 5 times 4 is 20. So after quadrupling 1 unit, we haven't even gotten to 26. So this has to be, x has to be bigger than 1, sorry. Or 1 has to be less than x. C, here we have decay. There's a mistake in the slide here. This should be 1/4, should be in parenthesis. So 1/4 to the x equals 3. So here we have decay. We started with 1. After 1 unit of time of decay, we'll have a quarter of 1, which is a fourth. But this is 3, so we're going backwards in time. So after negative 1, we would actually be quadrupling, going back in time, which would be 4 things. So this is somewhere between negative 1 and 0. And D, we have some growth. We start with 1, and then when is that going to be negative 4? Well, as 1's doubling, we won't get negative. And if we're halving in the other direction, it also won't get negative. Remember that b to the x, when b is greater than, b to the x, doesn't matter what b is. I guess it might. Yes, it does matter. So hold on, let's think about this for a second. So we had a times b to the x. If b is positive and a is positive, then a times b to the x was also always positive. And if we have a is negative, then we have a times b to the x is always negative. So the range of the output of an exponential when the initial quantity is positive, is always positive. So there's no answer. It's not in any of those intervals. There's no solution. So that's kind of a trick question.